This lesson is going to be working on what we call the empirical rule, the 68, 95, 99.7 rule. And we will also be working with the standard normal distribution, or how to use the Z table, or table A, from your book for statistics. First thing we're going to talk about is the 68, 95, 99.7 rule. When we deal with this, we are talking about your mean with how much does on average our other information, our data, differ from the actual mean. That's what a standard deviation is. To start, when you have a good bell curve, your mean is right down the middle along with your median. So you are zero standard deviations above and below the mean because you're right on the mean. If you go out one standard deviation either side, so I go out one, so plus 1, or I subtract 1, minus 1, standard deviation either side of the mean, that's where 68% of our data will fall. If I go out, so if I wanted to, by the way, I could go through and talk about it this way. This is 68% of our data because everything under the bell curve is 100%. Otherwise, we can go through and we can talk about if I go out 2 standard deviations either side of the mean. So this time I'm going to add 2 and I'm going to subtract 2 standard deviations. That's where 95% of our data should fall if we're talking about a good bell curve. If we go out 3 standard deviations either side of the mean, so this time I'm going out plus 3 standard deviations, or I subtract 3 standard deviations, that's where 99.7% of our data will fall, or approximately almost all of it. And then these points out here, this just continues out here as long as we want, without it happening, actually hitting the line, giving us room for that other 0.3%. Now, part of that sounds confusing, so sometimes it's easier just to walk through an example. So let's walk through an actual example. Women's heights follow a normal distribution with a mean of 64.5, that's a population mean, and a population standard deviation of 2.5. That's normally how we would write it out. A normal distribution with mu being your mean and your sigma being your standard deviation. So this tells me that right down the middle, for women's heights, it is 64.5 is the average female's height. If I go out 1 standard deviation either side of this mean, and the standard deviation is 2.5, so I add 2.5 and I subtract 2.5, that's where 68% of females and their heights will fall. So if I add 64.5 plus the 2.5, that puts me to 67 inches. If I subtract 2.5, 64.5 minus 2.5, that's what puts me down to 62 inches. So 68% of women fall between 62 and 67 inches tall. I can also go out 95%. If I go out 2 standard deviations either side of that mean. In other words, I need to go 2 2.5s, 2 standard deviations, and minus 2 2.5s. Why is there plus and minus? Because you have some people that are taller than 64.5 and you have some that are shorter than 64.5, and it should be symmetrical or the same on either side. So now I'm going to take my 64.5, which is right down the middle, and add 2 standard deviations, or add another 2.5 to the 67, which puts me to 69.5 inches. And subtract from the 62, which puts me down to 59.5. That's where 95% of females will fall, between 59.5 and 69.5 inches tall. If I go out 3 standard deviations either side of the mean, this time I'm going to go out 3 2.5s either side, because some are taller, some are shorter. Then that puts me started at 64.5 plus 3 2.5s puts me up to 72 inches. 64.5 minus the 3 2.5s puts me to 57 inches. That's where 99.7% of females will fall, somewhere between 57 and 72 inches tall. And you can always think about this in terms of a picture. 64.5 is the 50th percentile, so 50%. The blue represents 68%, or inside this bell curve, that's where 68% of females fall. I look at the red. This area right here is where, all that red is where 95% fall. And then if I go out one more, we'll do that one in black. That's this whole area right here. Fill that in. That's where 99.7, or almost all females, will fall, somewhere between 57 and 72 inches tall. That's called the 68, 95, 99.7 rule, or something called, some books will call it the Empirical Rule. The reason we look through that is to lead to something called the standard normal distribution. That is, the last one, the Empirical Rule, is just kind of a generic, what if we're 1, 2, or 3 standard deviations above or below the mean? Well, that's great, but what if I'm 1.2 standard deviations, or 1.3, or negative 4.7 standard deviations above or below the mean? Well, then that empirical rule doesn't help us. And what we need to do is solve for z. Z is, this is the equation. Z equals x bar minus mu over sigma, where z is our number of standard deviations that we are, standard deviations, above or below, depending on if it's positive or negative, the mean that we are. So z is the number of standard deviations. That's going to be key to remember. X bar is what we call our sample mean. It is usually what we are trying to test for, where mu is called our population mean. That is the mean that they will give us, saying here's what it is for the whole population of all females or all pieces of candy or whatever the scenario is. Where what we call sigma, looks like a cursive O, is the population standard deviation. And they will have to give you that in order to be able to fill this in or to solve for this. They'll have to know what the population standard deviation is. We then take this information, once you get your z-score, you look it up in a table, and then you can figure out your percent to be more precise. This equation, the z equals, is key. This is one of the most important things that comes out of stats, just because so many things come back to this equation and the concept of this equation. So it's going to be important to realize that z is your number of standard deviations, x bar is your sample mean, mu is your population mean, and sigma is your population standard deviation. That's going to be key to understanding. That leads to this type of table. Once we find a z-score, what we call a z-score, we can look it up in a table. Now, this table should be in your book. And in this book, there are two sides. There's the negative sides and there's the positive sides. This side is dealing with the negatives. This continues on. I just couldn't fit it on. But here's what happens. These two rows combined give me my z-score, or my number of standard deviations above and below the mean. In this case, it would be below because we're dealing with negatives. So if I want to look up a number, a z-score of z equals negative 2.91. Well, then I would go to negative 2.9. These two numbers are what I look up here. And because 1 is in the second spot, that's what goes here. I look up the 0.01. The 0.1 here is my key from this number. So 2.91 is actually this number right here, because we've got our 2.9, negative 2.9, and then we've got the 1 in the hundredth spot. So my percentile is 0.0018. This becomes my percentile. So when you're looking at this table, when you're looking at this table, you end up going through, and what you've got to remember is that outside here, this part right here, helps me find my z-score. And then anything inside the guts of this, anything inside here, oh, sorry, let's go back to that. Anything inside here, this is our percent, or our percentile. Key to remember that. And what you do want to remember is that this z-table, and they try to give you a hint using this picture right here, they try to shade and tell you this is the probability that you're finding. You're always finding from this number on down. That's what each one of these numbers do here in the table. This is the other side of the table, which deals with the positive numbers. Notice if you're 0 standard deviations, you're sitting at the 50th percentile. And then this continues on. Notice as you go further down this table, this number gets closer and closer to 1.00. So even though you might run out of table, it still continues to go on to 1.00. And again, it still finds from this number on down if you're looking at this z-score. Okay, so let's go through an example. I think that's easier, most things are in stats, is to walk through one example to see where numbers go. Women's heights follow a normal distribution of 64.5. This is our mu, and our standard deviation is 2.5. What percent of women are 58.1 inches or less? This is what I'm testing, the 58.1. So what I do is I draw my picture. Here's the mean, 64.5 is the middle. They're asking me about 58.1 or less. That's this area right here. That's what I'm testing. So what I do is I fill this information in. X bar is the 58.1. Mu, they gave me. So that goes in for mu. So 64.5. And it's important that you remember that the correct order, otherwise your answer will be wrong. This 2.5, or the population standard deviation, just goes to the bottom. So 2.5. That gives us our z-score. Mathematically, I would do the top first on your calculator, and you get an answer of negative 6.4 divided by the 2.5 from the bottom, and you end up with a z-score of negative 2.56. Well, I want to know what percent of females are 58.1 inches or less. That was the question. So what I need to do is I need to look up negative 2.56, this number right here in this table. So I'm going to go to negative 2.5. This is the row I'm interested in. And because 6 is our 100th spot, I'm going to follow the 0.06 down. And where those two lines intersect, this number right here, that is your probability. So my probability is 0.0052 that I would pick a female or find a female that is 58.1 inches or less in terms of height if all females average 64.5 inches. What about this type of question? Women's heights follow normal distribution. Same deal. What percent of women are 71 inches or more? So this time I'm dealing with this type of picture. 64.5 is in the middle, but I've asked for 71 inches or more. As soon as I shade to the right, that tells me to subtract my probability from 1. Let's see how this works. Z equals, let's fill in our numbers. I'm testing 71, so that goes in for X bar. Oops, goes in for X bar. Minus the mu of 64.5. They told us that. That was this part right here. Divided by the standard deviation of 2.5. That came from this number right here. Again, do the top in your calculator, and you're going to get an answer. And then divide it by the bottom, you get 6.5. Divide that by the 2.5, and you get a z-score of 2.6. So, or 2.60 in this case. Therefore, my probability is going to be what? We need to look this up. So I take and I look up I go to the positive side of the table, which is these numbers, not the negative, which was the last one. And here's the 2.6 row. And then I've got 0 in the hundredth spot, so I follow this down, and where those two numbers intersect, this 0.9953, that's my probability. However, that 0.9953 represents 71 inches or less. Remember, this table always finds from here on down. So what I need to do is I'm interested in the blue area right here, this upper part. So if you're telling me this is 0.9953, well then what's left over out of 1, or 100%, is this blue probability. So 1 minus 0.9953, which is 0.000047. That's your probability that we're going to find a female that is 71 inches or more. That's my final answer, is that 0.0047. Again, why did we subtract from 1? This table always finds from this number on down. So if I'm interested, it always finds from here on down. So 71 inches or less is 0.9953, but because they've said or more, and I've shaded to the right of my picture, then my probability needs to be subtracted from 1 like we did here, and you get your 0.0047. Okay, so what if they give me a question like this, where it's an in-between type of scenario? When we do that, we're going to go through, and what I'm interested in is 58.1 and 71. Between 58 and 71. So I'm interested, even though females in the middle are 64.5, I'm interested in this middle part right here, that in between. Well, we've already solved in the last couple frames here, we already solved for 58.1 on down. We already solved for 71 on down. And let's go back and check our answers. For 58.1 on down, we got 0.0052. So let's go back now. This was a 0.0052 probability for 58.1 on down. For 71 on down, we got 0.9953. So if I go back to this, I can do 0.9953. So what's in between? What's in here? That is going to be 0.9953 minus the 0.0052, which gives you 0.9901. In other words, there's a 99.01% chance I'm going to find, that's a percent of women, 0.9901 is a percent of women that are between 58.1 and 71 inches tall. Or 99.01% of women are between those two inches, 58.1 and 71 inches tall. So when you do an in-between, the best scenario in this case, again, I'll just redraw it, is if anytime they ask for an in-between, find this number on down, the lower number on down, find the upper number on down, subtract them to find what's in between. Not much different than if you were dealing with money. For example, if I told you you had 90 cents and you had to pay me 20 cents, how much do you have left over in your pocket? You'd say, I have 90 minus the 20 cents, which is 70 cents left over. Probabilities can be thought of kind of the same way, except you're dealing with a dollar being the whole bell curve, and everything underneath is 0 to $1 in terms of change. If that helps you think through probability, then use that as a tool. Biggest help in this case is to draw the picture. That is the key here. That makes everything a lot easier and helps guide you as to which direction you go. All right, let's try another example. This time you're working backwards. If I give you a percentile, it says women's heights follow a normal distribution, same deal. If a woman is in the 85th percentile, how tall is she? What happens is a lot of people think, oh, well, if she's in the 85th percentile, then that's the number that goes in for Z. However, Z is the number of standard deviations you are above or below the mean. They have not told me that. All they've told me is that we're in the 85th percentile. Now remember back at the beginning I told you that the percentile is in the guts. So what I need to do is go through this table and find where this table right in here, and I knew we're dealing with the positive because we're above 50%. Where in this table are we closest to 85% or 0.8500? And if you look through, it gets drops closer and closer. I see we are somewhere between 0.8500 falls between those two numbers. So think of this as 8508, and this one is 8485. This one is 15 units away, where this one is only 0.0008 units away, or 8508 versus 8485. So what happens is this answer right here, the 8508, is my best solution. That is my answer that is closest to the 85th percentile. So that's the number I'm going to work with. What I am looking for is to work backwards. This is 0.8508 is my closest, so I'm going to work backwards. 1.0 and then follow this up 0.04. So my Z-score for the 85th percentile is 1.04. Again, it comes from this number and then this being the 100th spot because I just worked backwards from where I'm closest to the 85th percentile. I work backwards 1.0 and then follow that up to the 0.04. So 1.04 is my Z-score. So these help find my Z-score, I should say. All right, so let's go back and let's fill in. X bar, that's what they're asking me. If a woman is in the 85th percentile, how tall is she? So I've got to find X bar. I don't know, so I leave that. Minus the mean of 64.5 divided by the standard deviation, which is, I can erase that because I know that now. So let's just fill that in. The standard deviation is 2.5. These two numbers came from 64.5 and 2.5. And at this point, you just do your algebraic or your algebra, just mathematically solve. So let me go through and do that. I'm going to multiply by 2.5 to both sides. That cancels those two numbers and leaves me with 2.6 on the left-hand side and X bar minus 64.5 on the right-hand side. I'm solving for X bar, so I'm going to do plus 64.5. And whatever you do to one side, you need to do the other. So I'm going to add 64.5 to the left side. These two will cancel. Leaves me with X bar equals 67.1 inches. So a female that is in the 85th percentile has to be considered to be about 67.1 inches tall. That is another way to work with this Z. So this Z, if we work backwards, this one problem I did was 58.1 inches or less. The second one I did was 71 inches or more was the key. So you got to subtract from 1. If it's in between, you have to solve for 2 of them and then subtract what's in between. If they ask you about a percentile, the upper 15th percentile or the 85th percentile, either one of those are the same thing. Upper 15th is the same thing as the 85th percentile. Well, then I need to go in, find where I'm closest to 0.85, work backwards to get my Z-score. That number is what goes into this spot right there. And then at that point, you just do your math and solve algebraically, and go through and algebraically solve, and you get 67.1, or your actual answer. So a female would be in the 67.1 inches tall range. Okay, when you're dealing with this table, just one quick note, when you're dealing with this table, you could be negative 50 standard deviations below the mean. You could be 5,000 standard deviations above the mean. But we run out of room in terms of a table. This table could go on forever. So what happens is anything past negative 3.4, so let's say negative 4.59, something like that. I go to look it up and I go, wait a minute, we're off the table. But notice what happens here as you go further to this direction on this table. This gets closer and closer and closer to a probability of basically 0.0. So anything past or under negative 3.49, we just say has a probability of 0. Same thing on the upper end. Notice we got 50th percentile. As we go with positive numbers, we go further to the right, we get getting closer and closer till it's 1.00. So anything that's 3.49 has a 0.9998 probability. So anything over that, we just say is approximately 1 or 100%. So don't let that throw you off. You go, well, it's not on the table. If I had a probability or a z-score of 17.13, doesn't mean you did anything wrong. It just means you're so far off the table that we'll just say a probability of approximately 1. So don't let that throw you off. All right, that's the empirical rule and the z distribution, standard distribution equation. Hope that helps.